Hey, welcome back to Trigonometry Part 2, and we've got some results here that you found from your sailing. I hope you like that. Did you get this sort of result? Okay, we're doing those scale drawings, and did you therefore see that every time you travelled on a 30-degree tack, the amount off course was about half? Half of 5 is 2.5, 2.9, might have made a bit of a slip there. Half of 10 is 5.1, that's pretty close. 15, 7.5, 20 is about 10, 25 turned out exactly right. So I might have made one little mistake there, I suppose you did too. But what did we find? It appears that when we create down here a right angle triangle, here we go, with 30 degrees, all those that we did, all those little constructions, the ratio of the side opposite, remember we were measuring this, that's the side opposite. Go into the angle and look out from the angle, and that would be opposite it, wouldn't it? That's the side opposite, and that's how much off course we were. And this was the distance travelled, which is the hypotenuse. It looks like whenever we have a right angle triangle with 30 in it, the opposite over the hypotenuse equals 0.5. Hey, that's an interesting result. But this is called inductive reasoning. We have actually just done a few examples and come to that conjecture. So inductive reasoning, this is important, this language for later on in maths. Inductive reasoning leads us to a conjecture, a proposition, which you may not believe because you only did a few examples. So what have we got to do as young mathematicians? We've got to go and try and prove that that's always the case. Okay, come down here. I've been doodling a bit here. There it is. We've been trying to see any patterns. See, these are all 30 degree and 90. So I guess they look very similar. I think similar is a key word there. And what do you notice? Well, hang on. If it's 30 in a right angle, there's a 90 here. All of these must be 60s. So actually, these triangles are what we say were equiangular. I've turned some up the other way down here. But they'd all have the same angles. And they therefore have the same actual shape, but different size triangles. And when you get sets of triangles like this, they're called similar. You can't say they're identical, they're only similar because they have the same actual shape. Okay, well that's interesting. We're on the way to trying to prove this conjecture, to understand why it must work. When you prove a conjecture, it's called deductive reasoning. So you might like to pause the presentation and write those things down. Deductive reasoning is used to prove a conjecture. Okay, so let's go and see if we can at least start on an informal proof so that we can say, hey, this ratio being a half for an angle of 30 in a right angle triangle, remember, will always work. Okay, let's come down here, and I've tried to draw all the triangles in a certain way here so they all line up. Can you see that this is possible? If you do like a nesting, these are all 60 in here, aren't they? So they're all actually perfectly the same shape, and it's like sort of stretching them out. Stretching this first one, here's the first one here. It's like fixing that point, fix your 30, and stretch all the little dudes out. What do you notice? To keep the same shape, that's to keep those angles the same, to keep shape, the amount of stretch on each side must be the same. The amount of stretch on each side, on each line, on each side of the triangle must be the same. Keep the shape. Okay, so what does that mean? Well, it means that every side here increases in the same ratio. So if that goes to there, then when you stretch it, that must go in the same ratio to there as what you're stretching this one. That looks like about 1.5 times. So if that goes 1.5 times, this must go 1.5 times as long. Otherwise, you will distort the triangle. And you haven't. They're perfectly the same shape. Same angles. They're all equiangular. So here, what we're saying, this process of stretching like this, where you fix a point and move all the other points in the same ratio, is called the process of enlargement. You're actually transforming the figure. It's a transformation of enlargement. You're going to shift every point in the same ratio. So let's do it again. This original line here, let's stretch it way out here. This is about doubling its size. And then this one here in the original triangle, let's stretch it out here. It will be about double. Hey, what do you notice? What do you notice? If in the original triangle you had a ratio of opposite over hypotenuse, let's call that the first opposite and the first hypotenuse. When you go out to the double, the top one is doubled in this last triangle here, and the opposite has doubled, and the hypotenuse, everything's doubled. What do you notice? Oh, it's the same ratio. So even if you take it way out here, which is about, hang on, let's get this right now. If you take it way out to the big one, which is about tripling this side and tripling that side, so all the sides are triple to keep the shape, then the ratio of the opposite over the hypotenuse, the opposite has tripled, and so is the hypotenuse. Hey, I think we just proved it. The original ratio, if it's 0.5 for a 30-degree angle, for one triangle, no matter how big you get it, okay, because they're all being enlarged in the same ratio, the ratio will stay the same, still at 0.5, because the sides all are stretched in by the same factor. So the ratio stays the same. Now that's an informal proof. That gives you some idea of what you're about in mathematics. If you think that it's a pattern, you make a conjecture, and then mathematics is about using some deductive reasoning, not examples, but deductive reasoning, deducing something that will all be true for all triangles. So it looks like we have got a simple, informal proof that trigonometry works, that if you have a right angle triangle and an angle of 30, the ratio will be the same. Now, do you see it? Okay, well, let's have a look. Here, does it have to be 30? Hey, no, it doesn't, does it? It should work. We could line up any size triangles. Should work for any, now it has to be a right angle triangle, so these all match up and are the same shape. For any right angled, let's use that abbreviation, right angle triangle, and a fixed angle. It doesn't have to be 30 degrees. 40 degrees should have its particular ratio. 50, 51. We should always be able to match the triangles up in this enlargement idea and use the same mathematics. Our little proof there. All right, let's come down and see what Pearson's have got to offer here. In these presentations, I'm going to be using the Pearson's textbook, Year 10. Okay, and it would be good if you had that handy by or an e-version of that. So, what are we going to say? Well, the book is saying even more. If we actually have a right-angled triangle, so here it is here, and we have an angle, any angle, the opposite over the hypotenuse, we've done this one, will be in a constant ratio. Hey, but because they were all stretched, the same, hey, the ratio of any sides. What about the adjacent over the hypotenuse? Will that stay in a constant ratio? Well, wow, it will. Because of the process of enlargement. All the sides of that triangle have been stretched or enlarged the same amount. So the adjacent will grow, but the hypotenuse will grow in the same ratio. And therefore, that adjacent over hypotenuse in the very little one will be the same as in the big one. Can you see it? And then what about the opposite over the adjacent, if we compared those? Yeah, because enlargement, increases the size of each side in the same ratio, then the original little one, its ratio, will be the same as the big one. Let's do it for something like opposite over adjacent. Let's put opposite over adjacent in triangle 1. Now, what's done here? Oh, it's been moved out. It's 3 times as big here, I reckon. So, in the big triangle, the angles are all the same. Got to have 90. Got to have a 90. Remember, got to have a 90. If we keep the angle the same there, its ratio will be 3 times the opposite. Everything grows in the same ratio. Well, how do you know? Because the triangles keep their shape. You can't keep the shape and have equal angles if one side stretches more than another. Look at this. What's your maths like? 3 times 1 over... Hey, if they've both been tripled, you're back to the original ratio. Hey, this is powerful stuff. We can say, if you have a right-angled triangle, all 3 of these ratios of the sides around any fixed angle will be the same. As long as you have this scenario. Let's just watch it now. It's got to be a right-angled triangle because we must set it up as equiangular. So it doesn't really matter what angle is in here. We could use the Greek letter theta to mean an angle. That's quite commonly done in maths. Now that means this will always be constant. You've fixed a 90 and you've got this angle. And now, so this angle will produce a characteristic set of ratios. Characteristic set of ratios. It's like a fingerprint, or like a DNA if you like, measuring the nature of your angle by the sides around it. And you can use any pair because of this up here. Okay, do you get it? I want you to see why this works, and now all we're going to do is follow it in the fashion of a rule and use it. And let's come down here and see what Pearson say here. Okay, so here's our final message. In any right-angled triangle, the sine, we call this the sin or sine of an angle. It's abbreviated, it's up here, the sine of an angle, the cosine or the tangent of the angle. These are the words that we use to say that we're looking at the ratio of in sine, the opposite over the hypotenuse. We abbreviate that to sin, we leave off the E, abbreviated to sin, and it's O over H. The cos of an angle or cosine is the adjacent over the hypotenuse, and the tangent, abbreviated to tan, is the opposite over adjacent. So what you need to do is try to remember, when you have a particular angle, a characteristic set of ratios will follow. Go to the angle, look out, the side opposite is what you see. The hypotenuse is always known, it's opposite the 90, or it's the longest side. And so what's left is the adjacent. I would not go into a triangle and try to work out the adjacent from an angle, because there's really 2 sides next to or adjacent to the angle. So I would do it by default. Okay, let's do it. Let's go here. So this is the angle of, let's say, 70 degrees. I go to the angle, I look out. What I see is always the opposite side. Go to the 90, this is the hypotenuse. Do this in these steps, and so this is the side adjacent to the angle. So little old 70 will have three characteristic ratios. Sine of 70 will be its characteristic opposite over hypotenuse, and we're going to find out in a minute. We go to technology here, because on the calculator is stored all the characteristic ratios for every angle and decimal parts of angles. Now, the next problem is, how are you going to remember which one's which? The sine, which is on the calculator, is the opposite over the hypotenuse. What if you're looking at using two different sides? These two. The ratio would be the adjacent over the hypotenuse. You'd need to know where to find that on the calculator, and you'd need to remember that that is the cosine. So here's a little method of remembering which one's which. It's called SOHCAHTOA. That's all the letters standing for the ratios. So the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. Okay, so really should put that, shouldn't I? So it helps you say, well, if I am working in a triangle with a particular angle and the sides I have are the opposite and the adjacent, let's have a look, the opposite and the adjacent, which ratio will I use? Oh, here it is here. Opposite over adjacent is tan, that's a TOA. So SOHCAHTOA is a useful tool for students to remember which way up and which pair of sides you're playing with. All right, let's come down here and have a look on the calculator, because here's the Casio. Pearson's uses the TI a lot. So on the Casio, go to Menu, highlight Run Math Mode, hit Execute, and we're into this window here. And can you see them? Here they are down here. Hang on, arrow down here. Here they are, sine, cos and tan. So you can find these ratios. All right, so you hit sine and up it comes. But you have to reset the calculator, because the angle must be in degrees. We're working in angles in degrees. You don't know, but angles can be measured in other units other than degrees. So I want you to hit Shift, here we are, Shift, and then Menu, which is the setup of the calculator. See it in there? Setup. So if you hit Shift and Menu, you go into setup mode, and here it is here. You want the angle to be in degrees. So you scroll down with this button here, highlight that line, angle, and make sure it's in deg. See here, down here, rad and grad, you don't want those. Radians and gradients. You'll learn a bit about that later on. Used a lot in science and engineering, radians and gradients. But deg is for degrees, that's what we want. So, you know, another student might have had your calculator who's in year 11 or something, and they might be using radians, so you have to reset it. So once you've reset it, you can then, you've got sine on the window there, you can hit 30, and it'll come up there, hit execute, and you'll see, oh yes, it worked. It's 0.5. Actually, if you set run mode up into, come back over here to this window over here, if you set math mode up, run mode in math format, that's that one there, you will get the fraction of a half display. All right, so we've got, what have we got? We can find what the ratio is for any angle of the opposite over the hypotenuse, which we're going to call sine, the adjacent over the hypotenuse, which we're going to call cosine, and the opposite over the adjacent, which we're going to call tan. Why is this useful? It's interesting, but why is it useful? Well, let's look at this. Hey, if you had a problem where you were trying to find a particular value, so let's have a look at this first one here, find the value of t, so that's this diagram here. If you said, I'm going to try and draw this triangle, how long will this side be? We can now find it. Did you realise that? So here are the steps. Very good thinking here from Pearson's. You think, now copy the diagram down. I'll go to the angle, I'll look out. Oh, that's the opposite, the T side. Go to the 90, that's the hypotenuse, and this is the adjacent. Now if I want to work out T, here's what I've got. I'm trying to find that. What's the only other side I've got? The hypotenuse. So let's write it down. I've got an angle of 34. The opposite is T, and the hypotenuse, hang on, we'll just get that back again here now, playing with me here. So here, and the hypotenuse is 25. Identify the trig ratio. What is it? SOHCAHTOA. Okay, well, let's see how we use SOHCAHTOA. So we've got an angle, and we've got, opposite and hypotenuse. Which one's got that? Opposite and hypotenuse. We need sine. So that helps you identify which ratio to use. You write it down, you put in the numbers, the sine of 34, well, we're missing this, have to put a letter instead of the number. And so multiplying both sides by 25, let's remember our algebra. T has been divided by 25. To get T back again, you'll multiply by 25. So here what we've got is that T is 25, now let's get this back again, 25 by the sine of 34, then we can go to the calculator and put in the sine of 34 is 13.98. This is magic because what we've got now is the ability to find a missing side in a triangle. Do you want to have some more fun here? Here's the other one that they asked, part B. Can you see here that we have a side, we have an angle, and the missing side is that one there, the longer side, the hypotenuse. Can we find it using our ratios? First thing, put down the angle, go to the angle, look in the triangle opposite it, that's the opposite, then assign the hypotenuse. And the one left is the adjacent. So what ones are we dealing with now? Well, we have the adjacent and the hypotenuse is unknown. So let's go to SOHCAHTOA to pick our right combination, our right ratio. So we have adjacent and hypotenuse. Oh, it must be the cosine. So we'll go and write the cosine is A over H, adjacent over hypotenuse. Stick in the number, cos of 49, the cosine is now, stick in the adjacent is 13.5, the hypotenuse is unknown. Now we'll go and try and rearrange this. So there are two ways of coming here. 13.5 is divided by x. We could reverse that by timesing by x and it'll come up there and it will be removed from that side. Opposite operations. And so x then has been times by cos of 49. To get x back again, we'll divide by the cos of 49. That's one way. Another way, if you don't like that, is to invert both sides. So if 13.5 over x is cos of 49, if we put both of them as reciprocals, this becomes that. Right? If we invert this side and put x on top, because it's easier to work with, we've got to turn this side upside down or invert that. Now, what's been done to x? Been divided by 13.5. To get x back again, we'll multiply by 13.5. So you get 13.5 divided by the cos of 49 is x. So you get the same result. Two different ways of thinking about it. Now we've got to go to the calculator. And the syntax would be 13.5 divided by, I'll probably just bracket this for a reminder, cos 49 and execute. Okay, and so we can find that side. It looks like we'll be able to find all the sides of a right angle triangle if we have one side and the angle. Okay, so let's go down and it's your turn in a minute. So here we are, to find an unknown value in a right angle triangle. This is probably worthwhile writing in your notes. Draw the right angle triangle showing all known information. This is important. And the unknown value labelled with a letter. Label the sides OA and H by following the steps. Look opposite the angle you're given. That equals O, the opposite side. Look opposite the 90. That will be the hypotenuse. Then part 3, remaining side is the adjacent. Okay, so that's a process by which you can work out O, H and A. Identify the trigonometry ratio, SOHCAHTOA. Substitute the known values, form an equation and solve for the unknown. So we need to practice that now. So I want you might have to rewind the presentation a bit to go back to that example. Here's your first set. So I want you to pause the presentation now and have a go, or in a minute. So I'll just come down here and make sure, as you forward it later, you can go to all of them. Okay, so just pausing it there so you can toggle on. And then I'll keep going because there are the answers. So when you've done a problem, toggle on to this point, check it, so there's A, check it, then go back, just toggle back to the beginning, do B, then toggle on to come back to here, that sort of thing. You can work quite nicely with that, or you could write them down. Okay, so there we have it. You could pause the presentation now and go on and try those. All right, I'm going to go on with the rest of the presentation because it's going to be exciting. And what we're going to do now is to say, well, that's all right, that's theoretical mathematics, but can we use it in the real world? And the exciting thing is we can. Here we have our problem. A 3.2 metre ladder rests against the wall, so its angle with the wall is 65. There we have it, a drawing. We need a diagram for a start. Must have a good diagram. How high up the wall does the ladder reach? Okay, so it's a 3.2 metre ladder, so let's label that. And we don't know how high up the wall. Could have called it H. They've called it D here. So we have our diagram with all the given information labelled on it. That's important. All given info labelled on the diagram. That's very, very important. Okay, so now we have a right angle triangle, presuming it's an upright wall, a vertical wall. So this does not have to be to scale, this diagram. Write down the known information. The angle is 65. Now, we go into the angle, we look out, that's the opposite. We don't have any information about that. We go to the 90, we look out, that's the hypotenuse. So the other one, this one over here, must be the adjacent. Do it by default for the adjacent. So you've got the angle, you know the hypotenuse, and the adjacent is what you want. So what are you going to use? Let's pick out the right pair. So the sine is the opposite over hypotenuse. We don't have the opposite. What have we got? We've got the adjacent and the hypotenuse. Oh, adjacent and hypotenuse, we'll use the cosine. So we write down the cosine is adjacent over hypotenuse. Put in the numbers now. The angle is 65 and the hypotenuse is 32. We need to find D. D has been divided by 3.2, not 32. So to get D back again, we will multiply both sides by 3.2. Solving the equations by inverse operations in reverse order. So D is this thing, and you would then put that on the calculator. So, are you getting excited? You can work out practical problems with trigonometry. Let's have a look and perhaps do another practical problem. A rectangular wooden frame has a diagonal piece of wood joining the opposite corners for support. The vertical height is 2.5. The angle between the diagonal and vertical part is 57 degrees 15 minutes. We'll talk about that in a minute. How long is the diagonal piece of the frame? Well, we're trying to get a strut in here to stabilise it. So we need to have this sort of picture. We put in the angle, and what other information? We know that the height of it is 2.5. So can we work out the length of the diagonal? Go through the same process. Write down the angle, go into the angle. The side opposite isn't going to be used in this problem, but we've got it. The one opposite the 90 is the hypotenuse, and so the other one remaining is the adjacent. So write down the adjacent, and the hypotenuse is going to be used because we have to find that. Write down Sokotoa and pick out the one that's got those two in it. What have we got? We've got adjacent being used and the hypotenuse, or it's cosine again. So you write down cosines, adjacent over hypotenuse, then put in the numbers or the letters that are unknown. Now 2.5 has been divided by x. Let's reverse that by multiplying both sides by x. Coming to this, it's 2.5. And then to get x, it's been times by cos of 57.15. So we will then divide by it. Or alternatively, let's go over here. Cos of 57 degrees 15. Let's put that as the reciprocal and find the reciprocal of the other side, which means you'll turn upside down. So x is now on top. X has been divided by 2.5 to get our answer over here. So to get x back again, we'll multiply by 2.5 and have this thing here equals x. Now 15, this little stroke here, Pearsons do talk about this. We haven't done that yet. That means 15 minutes. And this minute is a 60th of a degree. So we need to convert that to decimals by dividing by 60. So that will give you a decimal part of a degree. And here, of course, it's 0.25 if you do that. So the angle you'll put in will be 57.25 degrees. There is a button on the calculator which has got degrees, comma, comma, to change angle in degrees and minutes straight to a decimal number of degrees. Because when you're finding the cosine over here, you do have to put this in cos followed by the angle in a decimal number of degrees. So when you work that out on the calculator, we actually have this answer here. We'll just get rid of that. We have an answer here of 4.62. So let's now go down and see if you might be able to do some practical problems. The crucial thing here is to draw a diagram. Draw a diagram for each of these. I'll just get this going right here. So here we need a diagram for each of these. A diagram doesn't have to be to scale, but it has to represent what's going on. All the given information should be put on it. All info given should be put on it. And then you start working out what sides and using your process. So you might just come down here. You've got those three. Could pause it and have a go. And the answers are just down here. Okay, so you can have a go and just check your answers, toggle back. All right, so pause the presentation and have a go. I'm going to go on now with the final little bit, some more excitement in some understanding problems. So Pearsons has made this an MYP book by gradually building in more difficult problems that you actually have to think about. Just remember, you must always complete a 90-degree triangle. So this is not formed here. Complete a 90-degree triangle to use trigonometry. Okay, to use trig. All right, so you might have a look at that one and then go forward to the answers. I'm just going to toggle up here so you can pick a couple at a time. Here are the answers down here. So as you do question 5, that was the first one. Here's the diagram and some answers. And go down, I think go down to 9. What have we got? 10. Can we get 10 on there? Toggle there, do 9, pause it, and then we'll just come on to 10. Okay, and pause it and have a go. This hint is basically for the trapezium question, which I think is this one down here. Yeah, so this is the trapezium, little hint for the formula for the area. So you can then, if you like, toggle back. There's the answers there. We haven't quite seen all the problems yet, because there's some open-ended questions here. What Pearson's have given you a bit more of a puzzle question here, open-ended. Okay, so pause it there and try 12, 13 and 14. Notice a bit harder here because you don't have a diagram. You must always try to get a diagram, so I'll just finish that off. Okay, so there they are. So you might have a go at all 14. The last few, the open-ended ones, give other possibilities. Bit harder to think of, and you have to go through that with your teacher with the answers to this, because they've only got some answers here, there, and you might not be able to get those. All right, so have fun with that. I hope you're getting excited, because basically you now have a very useful area of mathematics in the practical sense. Very, very useful. All right, well, we're going to do more because, as I said, trigonometry is triangle measurement, and we might want to be finding missing angles. If we didn't have an angle at the sides, could we backtrack and find missing angles? That could be interesting in another presentation. So for the moment, it's cheers from me. Catch you in the next presentation.